Right, good afternoon, everyone. I have extended the deadline for the homework till Thursday for the homework 7. And the homework 8 is also due on Thursday. And as usual, the portal for homework 8 is open till Saturday, 12 p.m. But the homework 7 portal closes on Thursday. And it's already extended by a week. I won't extend it any further. Just because it's on Thursday, don't delay. Start early. So if you're starting just now, it's already going to be a bit tight. Do a good job on that homework because that's basically all this course is designing a controller for a DC motor. When you take the advanced electric drives, we'll design the same controller for an AC motor. That's about it. Right? As long as you understand that subject, AC motors are very straightforward. So take your time, do a really good job on the homework. Because it doesn't matter. That same homework is what you carry over for the project as well. So kind of amplifies the work you do there. Okay, there's one question in the homework 7, the last question, which asks you to find the steady state error for a step input without an I controller, right? Let's say this is our electrical transfer function 1 by SL plus R, and we have a PI controller, we have some voltage reference, and we have some current feedback coming in. Let's say this voltage, let's put some values to it. Let's say this is, let's use the one from the lab, 4 millihenry. Let's say this is 2 ohms, and apply a step voltage. Let's say it's going from 0 to 10 volts. Let's say I don't have an integral controller. What is the steady state current going to be? Oh, sorry, this would be current reference. My bad. Sorry. Let's say it's stepping from 1 to 2 amps. Okay. So I want the motor to generate 2 amperes current. Will it reach 2 ampere in this case without the I controller?
There's no EMF.
I ignore the EMF term for now. Let's assume the rotor is locked. Right? The rotor is not rotating, so the EMF term is not going to be there. Olivia, do you have an answer?
Oh, no.
Okay, Kristen.
Is steady state 0? We can see like when the error becomes 0. Is
Yeah.
there a steady state?
There will be a steady state. Because this is as long as the motor has realistic parameters, like all positive R, L, B, and J, DC motor always converges. If it converges, there is a steady state. Whether the steady state will match with our reference, that's a different question. That's the question. Right? So the question is, if I ask, so let's start with a simple one. Let's say there is the PI controller there. What will be the current at steady state?
Same as IREF.
Same as IREF. So if there is an I controller, whatever 2 ampere I ask here is going to be the same 2 amperes that's coming here and steady state. It will take a sweet time to get to there, right? And the time it takes would be dependent on the control bandwidth, that omega C we chose for the inner current controller, right? Again, here we are assuming mechanical speed is 0. Right? That's why the EMF term is not missing. But now I'm asking the question, what will it settle at if there is no integrator? If I just had a proportional controller, what will be the value it will settle down to? How would I go about finding it?
Final value theorem.
Final value theorem. So if we limit f of t as time t tends to infinity, it's just going to be limit s tends to 0, s times f of s. Right? So in our case, the one that we have desired is our f of t function is basically I of t. We want to figure out what the final value of the current is. T tends to infinity. What is my f of s here?
AP over SL plus R.
AP over is that it?
You close the loop.
Close the loop? Because the answer you gave, that would be the answer if this loop wasn't closed. Right? So we have a loop that's being closed. If the loop is not being closed, the solution is pretty straightforward. Right? It's whatever this reference times Kp divided by the resistance term. That would be a final steady state value. So if we close the loop, so this is our G of S transfer function. Our closed loop transfer function is going to be G of S divided by 1 plus G of S H of S. So Kp divided by SL plus R, the denominator SL plus R will get cancelled. So let me put it down. SL plus R. plus 1 plus g of s, SL plus r. So you know this will get cancelled, this goes to numerator, so all you're left with is Kp plus SL plus r plus Kp. Right, so this is a closed loop transfer function. Is this all f of s's? What is the f of s indicating? It's indicating I of t. My I of t is this closed loop transfer function multiplied by I ref. Right, so f of s is going to be equal to whatever my closed loop transfer function is, C of s times I reference of s. Right, so this product, this times this whole closed loop transfer function is what is giving me I of s, which is what I am calling as f of s here. Okay, what is my I ref of s? What will be the Laplace of the reference input that I've given there?
2 over s.
2 over s, it's just a step input. So if you take the Laplace of the input of time of t, that's just going to be 2 over s. So substitute all of those here. So this one becomes 2 over s. And then C of s I have here. So limit s tends to 0, s times 2 over s times Kp plus SL plus R plus Kp. Right, so as s tends to, so these terms cancel out, and as s tends to 0, this term goes to 0. So all you're left with is 2 times Kp divided by R plus Kp. In what scenario would I get the 2 ampere that I desired?
With the full PI control.
Without the integral controller, what characteristics should the motor have so that I get the same 2 ampere that I asked for it?
R is 0.
R is 0. Because the reason we added our inductance, our integrator, when we looked at our car example, right, is because of to overcome the friction. If there was no friction, once you get your desired speed, you don't need to apply any force on the pedal. So it's always the loss term. So in our case, the friction is the resistance in this case. When you do the same thing for the mechanical loop, your B is going to be the term that contributes to the steady state error. If the loss term is not there, for a step input for a first order system, doesn't matter, higher order system, so if the loss term is not present, for a step input, it will always reach steady state. But because of the loss element, you always need an integral controller as well. So in this case, it won't reach to steady state because of this R term. Right? If that term goes to 0, whatever 2 ampere I ask is the same 2 ampere I'll get with just a proportional controller. And that's why when you design your position loop controller, the transfer function for your position loop controller was going from mechanical speed omega to your theta, that was just 1 by s. There was no plus some loss term to it. All right, but if you say you had some kind of gear mechanism that can't hold the position in place, it keeps slipping, then that would be modeled as a loss term in the angle, right? Which will then cause a decay, which will then not make it reach steady state without an integral term. There you will then add an integral term. But for an ideal system, where you just your omega directly goes to theta, there's no gear mechanism or anything such type, which is deteriorating it, then you don't need an integral controller, again, as long as there is no external disturbance and stuff, right? So this is what you would want to answer for that question. It's a little bit more complicated. Jonah already jumped the gun and asked me the question. So the term that I had ignored there was the back EMF, right? I can't ignore the back EMF because I said I'm locking the rotor, but in reality, the rotor is going to be rotating as soon as I apply some reference. This again is IREF. As soon as I apply some current, I've started creating torque in the motor and the motor is going to start to rotate. So there's going to be an EMF term. How do I find the steady state error now? There's still going to be a steady state error. For the laser. How do I solve this? So if you just answer this part, I will ask the TA to give you the full points. But that would not be the correct answer though. Right? Because the EMF term starts to interfere with it. Right? But this is a very simple transfer function to simplify. So take this term, put it into here, right? And you can reduce this even further. So you have plus Kp coming out, some positive, negative, 1 by SL plus R gives you your current. It's the same current that gets multiplied into this and comes down. Oh, there's a Ke term, sorry. Right? Comes back as Ke term. So let me take this Ke and move it here as well. So I have Ke Kt divided by Sj plus B. Right? And now what I have remaining is the same current term is getting multiplied by Ke Kt Sj plus B, giving the EMF in the end and closing the loop. There's one assumption I made here that the load torque is zero. Right? If the load torque is not zero, that complicates the picture even further. That's another term that needs to be included into the system. We'll get to that in just a second. Once I have this, can I solve this? Can you find the closed loop transfer function for the system? Pretty straightforward, right? This is G of S, this is H of S. Closed loop transfer function is G of S divided by 1 plus G of S H of S. Then you'll have some kind of closed loop transfer function C of S. That times my step input. In this case, it was 2 divided by S. This is going to be my whole F of S. Multiply this by S and put limit S tending to 0. That will give me current at time t equal to infinity or I steady state. Right? If I had load torque as well, how will I solve this? What is the characteristic of the system? The equations I have written for the DC motor, if you had to qualify it as a class of systems, what do you call it as? Control system, where these linear systems or non-linear systems?
LTIs.
Linear system. So we have a purely linear system. So what is the property we can exploit in a linear system?
Superposition.
So version, perfect. So if I need to figure out what will happen when there is a current reference being given, as well as there is a torque present, first solve as if the torque is 0 and figure out what the current is going to be. Then assume the current to be 0. Right? So this loop just disappears. Just a negative gain 1 coming into here. And there's going to be a torque input here. So we have Kt, positive, negative, tau L, then 1 by Sj plus B, and K. And this input has gone because the reference current is 0. The feedback current is just being negated, so this negative 1 can just be clubbed into this minus Kp as negative Kp, right? And then rest of it, so now your new input is tau L, and then you do the same simplification that we did here, just move the terms around so that you get a relationship between the tau L and the current. So you want to figure out the relationship between tau L and the current. So move the whole diagram around so that you have the input as tau L and the output as the current. You'll get some kind of transfer function. Apply the same thing. Find the steady state value for that current given the torque profile, whatever the torque is required. Right? And then once you have the current, how do I get the total current? When I have the load torque as well as the reference current, what will be the final value? Yep. Superposition, right? Some of the two. That's how we are able to do this. So when you make this current 0 and you had only the load torque, you get some current, some I due to tau L. And then when you make, so this is when I ref is 0. And then you'll get the same thing, some I due to I ref when tau L is 0. When neither of them are 0, when I ref is not 0 and tau L is not 0, when both of them are present in the system, it is just a sum of the two due to tau L plus I due to I ref. Right? So that's what our linear system can guarantee for us. Right? Maybe any questions? Yes,
So is effectively like the load torque taking away the current, what the sum of current without.
It's not taking away in that sense. It's this is so without the presence of the reference current, you just had some motor model which is closed on in itself with a feedback loop. Given a load torque, it would have settled to some current. If this is not there, given a reference current, we already saw it would have settled to some other current. Now, in the presence of both, it's just going to be the sum of the two. Okay. That's the same thing you do in circuit analysis, right? We had a voltage source like this, and another voltage source on the other side.
Yeah.
The way you always short this, find out the current through this network. Short this, find out the current through this network. The net current is sum of the two. Only possible in linear circuits. Okay. Any other questions? Okay. So there's one more thing. In so far we have just looked at the theory of the PA controller. When we implement it in hardware, we would want to do for the integral loop. There's a little bit of a problem there. Yeah. So there is some error. So let's just think of the current loop alone. So this output would be some voltage. And initially, if say my motor, I want to get to 100 radians per second. Sorry, if I want to get the current to, let's say, 5 ampere, then my current actual is, let's say, yeah, it's going to be 0 ampere at time t equal to 0. And if my Kp value, let's say, let's put a reasonable value of 25 or something, right? It's going to ask for a current V of 75 volts. Because I have 5 ampere coming in as the reference. The actual current is 0 ampere, the difference is 5, Kp is 25. So this output integrator is just starting up at time t equal to 0, integrator output is going to be 0. So it's going to initially start asking 75 volts right away. As you've done in the lab motor can only take 40 volts, the power supply is only 40 volts. There's no way I can generate 75 volts from our inverter. So what can I do to modify that? Now we are no longer in the linear domain, we have to go to non-linear domain. And what will we do to so that we don't ask more voltage from the power converter than it can generate? What tool would you put there so that you don't exceed the voltage? What was it?
Saturation.
Saturation. So what you're going to do is put a saturation here, right? And set the saturation limit to 0 volts. Or actually, we have a H bridge in the lab, so we can generate both positive and negative voltages, right? So we can go up to negative 40 volts, and we can go up to positive 40 volts. So that the power converter is never asked to generate a voltage greater than it can generate, right? There is still a little bit of a problem here because we have already reached the 40 volts that the power converter can generate, but the integrator does not realize that, right? So what the integrator is going to do is, even though this has already tapped out its maximum, the Kp value, this is still going to keep integrating the error because it's 5 amps required, 0 amp currently, so there is an error of 5, and with time that's keep on going to be integrating, right? So this is going to keep on integrating. So this value, if you look at it, will start at 0, and it will keep going up and up and up. And this is called wind up. Because it's like those toys that you would have played as a kid, right? You take maybe I'm too old, I used to play with these toys as a kid. You have these screw kind of thing that you can wind it up. And there is only like 3 or 4 turns you can do, after which it's just useless. You can wind more and more. It doesn't add any value. There's a spring that just breaks contact after that. So the same thing happens. It's like after the output has reached the maximum value, the saturation block the converter can do, if this integrator keeps on getting more and more further, it's just getting wound up more and more without actually creating anything. But there is a very big problem with this because it has built up all this error. Let's say it keep on builds up. And let's say my motor current was initially 0, and then the motor current has reached 5 ampere. And once it reaches 5 ampere, my proportional controller would go to 0. My integral controller should have gone to some reasonable value, somewhere in the lower limit, like a couple of volts, so that it can continue to sustain that 5 ampere at steady state. But the problem is because of all the error before, it integrated and got wound up to a very, very large value. Now what it's going to do, it's going to drive the motor well past 5 ampere. It's going to overshoot. It'll go to 7, 8, 10 ampere, whatever it is. Right? And then what happens? Let's say this becomes 10 ampere. Now the error has become negative. So the voltage will go negative. And that keeps happening where now this integrator will come back down to 0, and it will get wound up in the other direction. Okay, so our current is now going to come to 5 ampere and then go down further. And then the same thing happens again and again. It's going to get wound up and down, and your current is going to enter what is called as limit cycles. Right, so when you study nonlinear control system, you look at the theory of how to figure out how the limit cycles occur, but intuitively that's the way it works out. Alright, so you're basically an integrator. If it keeps integrating past what the voltage limit of your converter can do, it is going to end up going into this wind-up situation where you're going to end up with these limit cycles where current keeps oscillating, though you should have reached steady state. How do we fix it? Any ideas?
Put a saturation here, like the line of your KI.
The line of my KI. Do I just put a saturation here?
Yeah.
That would still be a problem, right? Let's say I put the saturation at 5 ampere, which is my motor limit. 5 ampere times KI. So once I have that error 5, it is still going to be a constant 5 input to the integrator, which is going to keep on winding it up further. You're on the right track though. So in MATLAB, if you look at integrators, there's an option called anti-windup. Or even in the lab, when you do the hardware portion of the experiment on week 3 of a project, we will set this anti-windup turned on. So what it does is, you can set the anti-windup limit, same as saturation, but it does a little bit more complicated. So let's say I set the upper limit for the anti-windup at 40, lower limit at -40. So what it'll do is after the integrator has reached a value of 40 volts, the output of the integrator has reached 40 volts, no matter what the input is, it'll stop integrating. It just won't do any work after that. All right? Until the error becomes negative. So if it has an error which can pull it down from 40, then it will go ahead and integrate. Until then, it will stop integrating. So if the integrator has reached 40 volts output and the error is positive, it won't integrate any further. If the error becomes negative, then it will bring it down, so it will start to integrate. Same thing again, if it reaches negative 40 volts and the error is negative, it will pull the output further down, so it won't integrate at all, it will just stop integrating. Once the error goes positive, it will start integrating back up again. So that's called the anti-windup, right? So this is exactly what you have in those toys. When you twist them, they have this anti-winding mechanism where there is like a latch. So once you reach the limit, as you keep twisting it, you'll hear the gear sound grr, grr, grr. And then once it starts to hit the limit, you'll say that click, 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 click. There is a latch that basically disconnects the input from the output, basically preventing this anti-winder from happening in your physical system. So we are doing the same thing in the mathematical world as well to avoid that wind-up from happening, right? So the name comes from basically those toys that were there back in the day. Wait, anybody got any questions?
So instead of going like a triangle, it just is a straight line.
Yeah. So once we put that anti-winder, this limit cycle disappears away. So we'll go and settle down 5 ampere. Any other questions? All right, so okay, so that should basically, so these two parts should answer your final question. If possible, just a 2-point question, so I don't want, I wouldn't reduce any mark if you just gave me this as the answer, but do put the time and try to see if you can solve it this way, because that would be the correct answer. If you look at your simulation and take out the KI value and you figure out the value from this method, it will still not be correct. If the load torque is 0, you'll get the correct answer, but once you put the load torque, the steady state current will change with just a pure proportional controller. So for that one, you need to do supervision and figure out the correct value. But if I ask you in the exam, definitely do the correct method, not the half answer work. Okay, so next week we are going to be looking at AC motors. So let's just quickly brush up some of the concepts from AC circuits for today. We'll keep it pretty simple. And the homework for today is basically just this question, homework for this week. So at time t equal to 0, I'm going to be closing the circuit. I have some voltage V, Vm sine omega t plus some phase angle theta. So at time t equal to 0, the voltage is not 0, it's some value. And I have some resistance and some inductance. So I can write down the equation for this. So we have Vm sine omega t plus 5 is Ri plus L di by dt. At steady state, what can I tell about the characteristic of the current at steady state? Does anybody already know the solution for the current? The transient response of the current can give you the equation. Thomas?
Did you just short the inductor?
No, for the transient response, the full equation that evolves.
Oh, I don't remember.
Okay. So yeah, let's start off with the steady state then. What will be the current characteristic? Just the same sinusoid with some phase shift. Okay, so we'll end up with some R Im sine omega t lagging by some angle phi, right? It's an inductive network plus minus L omega Im cos omega t minus phi, because I'm assuming the current at steady state is going to be of the form sine omega t minus phi. So if I do the differential, that's just going to be cos omega t minus phi, and omega comes out from d omega t by dt, right? Everybody clear so far? What will happen if I replace this voltage source with cos omega t? So what will be my result? In that case, we have Vm cos omega t plus phi equal to R times Im cos omega t minus phi. Is this assumption okay? If I did nothing, I just made the phase shifted. So if I phase shifted this initial voltage source, which was sine omega t plus theta, by an angle of 90 degree, then I would assume the current would also phase shift by an angle of 90 degree. Right? This is a linear circuit, so the phase angles are preserved. Whatever the previous expression was, the same expression I should get. Frequency does not alter the way the network operation, or the phase does not alter the network operation. Right? As far as the final expression is concerned, the magnitude themselves would change. So, right? And then this term would end up being plus omega L Im sine omega t minus phi. Is it the other way around? Sorry. So when I differentiate the sign, that will be positive. When I differentiate the cos, that will be negative. So in this case, I assume in the case 2, and this was case 1. So for case 2, I assume Im to be cos of omega t minus phi. Right? So through this next half of the course, we are going to be using a concept called phasors and space vectors. We are going to be analyzing the AC motor purely in steady state. We are not going to be looking at the transient response of an AC motor. That we will do in the advanced electric drives course if you take it next semester, hopefully. So we are going to be looking at purely as phasors. And so we are going to use these two expressions and come up with a notation for phasor. So what we are going to look at is, initially we had a circuit which had some voltage Vm sine omega t plus theta. And then we're going to take the same circuit and now put some kind of other voltage which is 90 degree phase shifted, right? Once you have done that, what we're going to do is we are going to take this voltage, multiply this first term by j and add it up with the second term, just so that we can mathematically simplify, and we'll see what mathematical simplification we'll get in a second by doing that. Take the second voltage, add it up with j times the first voltage, right? So if you collect the left-hand side terms, you have Vm cos omega t plus theta plus j times sine omega t plus theta is equal to R times Im, same thing, cos omega t minus phi plus j sine omega t minus phi. Then I have plus omega L term is constant. I can take them out. Im term is also constant. I have j cos omega t minus phi minus sine omega t minus 5. And because the first term has the negative term, that hence I put it in the second term. And then the top term was just positive, so I just put it here. What is this? How would the term on the top of the brackets come out to be? It's a very famous formula, right?
E to the j theta.
Thank you. E power j omega t plus theta. Right, so we are going to write them down as e j omega t plus e j theta. And then, of course, this reduces to the same thing. It's the same as one on the top. So e j omega t, e power j theta. What does this reduce to? Well, I need it of the form cos A, cos theta plus j sin theta. Right, so I have a problem. The j is in the cos term. So what I can do is I can remove the j out. What would this term then become? Okay. Right, because j times j, you will end up with minus 1. So we have that. And this again becomes e power j omega t, e power j theta. J psi, sorry. E power j phi. And the angle here is minus 5, angle j was theta. Okay, so let's put them all down. So we have Vm e power j omega t, e power j theta equal to R Im e power j omega t, e power minus j phi plus j omega L Im e power j omega t, e power minus j phi. So right away, we can cancel the j omega t terms. Right, so the primary reason I did the voltage, second voltage plus this first voltage is because I can remove the frequency dependence when I go to the phasor domain. All right, this whole equation now becomes a nice linear equation. So that I can solve it pretty quickly looking at the phasor diagrams that I'll draw in a second. So that's the whole objective. But then of course we change the voltage. The voltage we would be given as some kind of real voltage, some cos omega t plus psi or some sin omega t plus psi. So what allowed us to modify it into some other complex voltage is just a pure mathematical assumption. We're going to assume, given any voltage, we can assume an voltage that's phase shifted by 90 degree, multiply by the j, add them up together, and solve the solution in the complex plane. And to get the real solution, what I'll do is I'll just take whatever solution this comes out to be, I'll just take Vm's cos omega t, just the real part of it alone, and call that as my solution. Right? So that's the advantage we get by going to this phasor. So the expression that we have now is Vm e power j theta is equal to R Im. I can take out Im common outside minus j psi times R plus j omega L. Okay. From this I can get the magnitude for Im, or let me rewrite this as Im e power minus j psi is going to be equal to Vm divided by R plus j omega L e power j theta. So the magnitude of Im is basically taking the magnitude of this whole term. Magnitude of e power any number is just the unit circle. Right? The whole term e power j theta is just the unit circle in the complex domain, real, imaginary. Right? So the magnitude of it is just unity. So this term magnitude is unity, so it's just Im magnitude. It's going to be equal to same thing applies here. If I take the magnitude of this, e power j theta magnitude is 1. So it is just the magnitude of Vm divided by square root of R square plus omega L square. So whenever we had AC circuits and we use this as the impedance term R plus j omega L, and this is the magnitude of, that was all because of this simple expression. Okay. Very disastrous. And the angle itself that we get is going to be, so if you look at the angle, e power negative j psi is going to be equal to whatever the angle term that's there on the right side, e power j theta times the angle of this complex number in the denominator, r plus j omega l. So if it was on the numerator, that angle would have just been e power j tan inverse omega l by r. Right? Since it's the denominator, you take that exponent to the numerator, that becomes a negative thing. So we end up with e power j theta minus tan inverse omega l by r, or basically the angle by which e power minus j psi, or the angle by which the current lags is going to be theta minus tan inverse omega l by r. If your voltage started at time t equal to 0, if it was at 0, right, for sine omega t plus theta, if the theta was 0, then the current is going to be delayed. The current is going to reach at 0 at some time later, which is given by this phase angle tan inverse omega L by R. Right? Everybody clear so far? So once we have this, when we go to AC, when we analyze induction motor and permanent magnetic synchronous motor, we are no longer going to talk about the circuit elements, right? Because it's unnecessary complication that we don't want to get involved with. So what we are going to look at these things are, given a voltage, let's say our voltage is some Vm sine omega t plus, let's say the angle is 0. So the angle is 0, I'm just going to draw it as a complex number, or let me start off with cos omega t. It's a little bit easier to visualize because then you put j sine omega t and the e power j theta would be the same as this theta I'm choosing, which is irrelevant in any way. But so if we start off with Vm cos omega t, the way I'm going to be solving is I'm going to draw a phasor Vm along the angle 0 degree, right? Because my theta is 0, so my e power j theta, that term is just a vector of 1 along the angle 0 degree, and it's scaled by a magnitude Vm. Okay, so that's all I've drawn here. Vm e power j theta is basically this vector. Now, what is my current going to look like? Well, we already have an expression for current. Im is Vm divided by square root of r square plus omega L the whole square. That's the magnitude part. And the angle is tan inverse omega L by r with a negative on it because it's lagging. Okay, so this angle, negative tan inverse omega L by r, is a angle phi, right? A phase angle going the opposite direction because negative value. And this is going to be a magnitude of vector Im itself. Right, so going forward, we're only going to purely look at phasors in the AC motor and not talk about the circuits. And we will look at how the voltage on the rotor varies and voltage on the stator varies. So to figure out all the voltages, the math again is very straightforward. You have a voltage vector Vm, you have some current along this direction. If I multiply resistance times Im, resistance times I, where is that phasor going to come out to be? Where will I draw the phasor for the voltage drop across the resistor in that circuit? Same direction as the current. We are scaling the phasor. Right? So this is going to be R times Im. And if I want to figure out what the voltage drop across the inductor is going to be, that's going to be j omega L times the current I. Right? The j part basically says if the current is in this direction, the j part multiplication basically rotates it clockwise to 90 degrees. Right? So your j omega L times Im is going to be 90 degrees. And the sum of the two, of course, has to be equal to Vm, the voltage that we apply. Right? So this is a very simple circuit that I took RL network. But as we go to AC motors, the circuit will get a little bit more complicated. And there, how much voltage drops, along which direction it drops. We have some leakage inductance on the rotor, leakage inductance on the stator, and the voltage keeps moving around all over the place. And we'll extend this a little bit further. So this is a static diagram. We'll extend it to something called space vectors a little bit later, next week, where we look at this whole phasor diagram starting to rotate in space. Right? So the idea is, and each of these vectors won't stay in place. They'll keep moving all around. But the idea is that some of them would have to end up satisfying all the KVL, KCLs, whatever we have learned before. Right? Just because we have this complex term introduced, that doesn't mean any of the other terms would be violated because it has a real physical connection to the real world that we have there. Right? Any questions? Okay. So for the same circuit that I have on the left there, what will be the real power for the circuit that I have here? I guess you have all the values that you need to have. Let's say the current magnitude is Vm. The current magnitude is Im, the voltage magnitude is Vm. Let's say the current lags the voltage by some angle phi. What will be my power?
Yeah,
Vm Im. That's it.
Wouldn't you multiply it by like the phasor,
By the
by the phase angle?
phase angle. So Vm Im cos of the phase angle. If these Vm Im are not in the RMS but the peak values, then the whole thing must be divided by 2. If it's the RMS, you don't have to do anything about it. The reactive power itself is going to be Vm Im divided by 2 sine of phi. Why is this cos of phi? Why is this sine of phi? The real power being cos of phi is pretty straightforward, easy. Can anybody give me the answer? What does the real power signify?
Power consumed.
Power consumed, and how will you get that value? So you have the expression for the voltage, time response of the voltage, time response of the current, and we had a definite, we did not even define, we derived the definition of power in electrical circuit in the electromagnetic theory class. It was V of t times I of t, right? How does that relate back to this term? Vm Im by 2 cos phi. Anybody? So if I look at the, let's say my network is just a pure R network without any inductance. It's just a pure resistor and I apply some sinusoidal voltage across it. So that's the sketch on the top. That's the black line is the voltage. Let's say it's 1 volt. And let's say the resistance is 1 ohm. And the current ends up being 1 ampere. It's going to be perfectly in phase. Right? So if you look at the power, we have a definition already. We have a derivation already. That power at any given instant of time is I of t times V of t. Okay? That's something we derived from our mechanical system, where we had mass times the velocity. Right? From their derivation, we figured out how to get the power in terms of the electrical circuit as I times the voltage. So once we have that, we can plot at every single instant of time what the power is going to be. So here it's going to be 1 watt, 1 times 1. And when both the current and the voltage goes to 0, power goes to 0. When they both go to negative, the negative product is again positive, and you end up with this diagram. So what you have there is basically product of cos of omega t times cos of omega t. Right? And you can apply cos A plus cos B plus cos A minus cos B, whole thing divided by 2, just split the term out. This is what you'll end up with. 1 plus cos to omega t divided by 2. Right? In my case, I assumed voltage and current to be 1 and 1. But if you assume the voltage to be some Vm and current to be Im, you would have Vm Im. And here you would have Vm Im as well, just the outside. Right? Over a full cycle, what will the integral of the second term be? Cos to omega t, if I integrate it over a full cycle back to Fourier, what will that answer be? Over a full cycle?
0.
0. So if I integrate this over a full cycle, the second term becomes 0. The only term remains is this half. Right? So Vm Im divided by 2. So that's basically the average value that I'm talking about. So the real power that I've written there is basically the average value. In case of a resistor network, there's just Vm Im divided by 2, which is V by root 2, I by root 2, which is the VRMS, IRMS. Right? Now let's take a look at what happens when we have purely inductive network. So in case of purely resistive network, the power is always positive. Right? The energy is always flowing into the load, nothing is coming back to the source. When we have an inductive network, same example, we have the voltage 1 volts and we have our current which is 1 ampere, which is going to be completely phase shifted by an angle of 90 degrees. Right? Because this term, if it is 0, the tan inverse of infinity is going to be negative tan inverse of infinity is going to be negative 90 degrees, and which is exactly what I've drawn here. Phase lagging by 90 degrees. Now if you look at the power again, same idea, the current times the voltage, you end up with this waveform, which is basically sine 2 omega t divided by 2. Right? So what happens is every half cycle, the power is being pushed into this inductor, And then the other half cycle, other quarter cycle, power is being pulled out of the inductor, power is being pushed into the inductor, power is being pulled out of the inductor. If you look at the energy, right, during this half, the power is being, so let's start from, right, from this edge to this edge, the energy is increasing in the inductor. And from this edge to this edge, power is being pulled out of the inductor, so energy is reducing. Right? So basically the energy going into the inductor is always going to be some value which is going in, and then energy is coming out, going in, energy is coming out, going in, energy is coming out. Inductor is not, you can't have negative energy because inductor can't generate energy in any sense. Right? So when people say energy goes back and forth, that is not what happens. The power flows back and forth between the source and the load. Right? The energy doesn't. The energy is going into the inductor, being taken out of the inductor, but there is no negative energy coming from the inductor. Right? So when we have our pure inductive network, the power ends out to be sine 2 omega t divided by 2. When we have our pure resistive network, is 1 plus cos 2 omega t divided by 2. When you have a combination, in our case, we have our RL network, the power ends out coming out like this, because wherever the current and the voltage are positive, we end up with positive power. Whenever the current and the voltages are negative, we end up with positive power again. And during the tiny portion where the current is positive, voltage is negative, or the voltage is negative, current is positive, we end up with negative power. If you break this equation down into constituent elements, you can break it down into two curves. One is, you should be careful where the phase alignment is. One is this waveform, which is the one on the top, 1 plus cos 2 omega t divided by 2. And the other one is this element, sine 2 omega t by 2. So the net power that I see here is just some fraction of this plus some fraction of this. So you can do the math and figure that out what those values come out to. So that power, the curve that I've drawn here, that P of t, that comes out to 1 plus cos 2 omega t divided by 2 times cos 5 plus sine 2 omega t divided by 2 times sine 5. Okay? So the cos pi term in our real power that we have there, that is just measuring how much your power going into your network is behaving as a resistive network. Right? This is the only portion of the power that actually gets fully consumed. Right? The other portion of the power is taken and given back, taken and given back, taken and given back. It's not drawn from the source in any way. But it is quite a bit of a problem when we have power system. In power system, we always try to make our loads behave at unity power factor. What is the reason? When you learn the power system course, you would have learned that unity power factor is some of the desired characteristic of a load. In fact, in industries, if your load is not unity power factor, your grid will penalize you for how much of a reactive power that you consume. And it's quite expensive. What's the reason? So now you're working with Doppler, right? What's the reason?
I squared R losses.
I square R losses. Because if you end up having reactive power being consumed by the load, to transfer the same amount of real power, you need to push in more current. Right? Because only some portion of the current is actually doing the real power portion, rest of it is doing reactive power. So you have more amount of current flowing in the coil to just push the same amount of energy out to the load. While in the previous case, if you just had pure unity power factor, you wouldn't have had that additional amount of current carrying the reactive power. Right? So when you want to reduce the current, because you end up with a lot of losses. There is another big problem. It's not just the I square R losses, which is not significantly that large compared to the load consumption. There is another bigger problem. What does that current do? That increased current, what will it do to the voltage?
Also like phase shifts all the voltages in the network.
Phase shifts and cause a reduction in the voltage magnitude. Your voltage starts to droop, right? Chances of your voltage, when you have more and more reactive power, you end up taking more current to get the same amount of energy into your load. So when you have more amount of current, you lose more amount of, you drop more voltage on the line, not just the IR drop, right? Your inductance of the line, that also drops a whole bunch of voltage. So you would expect your voltage to be 120 volts RMS, but you could end up with 110, 108 or something. And there's quite a bit of problem like countries like India where there's unity power factor, at least back in the day, was not enforced too strictly. So we can see many days where the voltage would drop a lot, right? It's called voltage reduction. If it gets too serious, it will be brown out. If it gets very serious, it will be called blackout. And the way we'll fix it is put an inductor right next to a capacitor across the load, capacitive compensation, so that the reactive power comes from the capacitor and not all the way from the transmission line energy source, right? So what we are trying to do is when we have this RL node, we are breaking the power into two components. One power which behaves as if it's a pure resistive network, another power which behaves as if it's pure inductive network. This portion of the power is something that we desire that needs to be sent from the energy source. This portion we usually try to avoid and keep it local, right? And we want to quantify the measure of that power, right? So the sin phi term that comes here, so the whole thing again has the VMIM term, right? So VMIM sin phi divided by 2, that is the qualification for our Q. While the real power is a physical entity. This times VMIM. Or you can take this whole term and the integral over one single cycle. That is going to be, this term goes to 0. So it is just VMIM divided by 2 times cos phi. Alright, so the sin phi for reactive term is not some kind of pure mathematical invention. It is basically a method to quantify the amount of power that the actual reactive element is taking in and giving back. Okay, and okay, so anybody has any questions on this part? Okay, so we are in our case we are going to be always working with 3-phase AC motors. We will look at the brief operation of a one-phase induction motor when we learn about induction motor. But why is the transmission line 3-phase? Why do we transmit power in 3-phase, not as just a single phase?
Does it not require like return paths?
It does not require a return path. We still require a return path for that too. So in a 3-phase network, whatever current goes in one terminal, the other two terminals are going to carry the current out. Right? You don't need a neutral wire if it's balanced. Yep.
The average power is equal to the instantaneous power.
Perfect. Average power is same as the instantaneous power. So the biggest problem with the power that I drew there is it's pulsating. Right? You saw the, even in the resistor case, we saw the power, that power is pulsating. If you were to try and connect that to a motor, our torque times our omega doubles the power. Let's assume there is no power lost in the friction, there is no power lost in the resistance. This must be equal to V of t I of t. Now, let's say your load torque. Let's say your load torque is a constant, but your voltage and currents are varying sinusoidally. Then your power is varying as a second order harmonic component of 2 omega t. What is going to happen to your speed? It's going to start to fluctuate, right? If only this term is constant, and if this term is constant, then your omega can remain constant. If this term is some constant, and this term is oscillating like this, then our speed would have to oscillate. Okay? Because this oscillation divided by a constant is going to be the oscillation again, and this is what your speed is going to look like. And this is a big problem. That's why when you have your industrial motors, you would hear them run very quiet. Such a high-powered motor would be very quiet. But if you have your ceiling fan at home, it's very low power and it will still make a lot of noise. That is because of the vibration coming from this, because it's running out of a single-phase power supply. A single-phase induction motor cannot self-start. We'll get to how that problem is addressed in a ceiling fan. So it's a pseudo single-phase during startup, but at steady state will run a single-phase and it's going to have a lot of oscillation in the speed. If this is how it's going to look like, what can we do to address it? How can I smooth? If this is what it would look like, what can I do to smoothen the speed? Let's say I can't change anything on the electrical supply side. It's going to be single phase. There's nothing I can do. What can I change on the mechanical side so that I can remove a lot of oscillations in the speed? Where is this oscillation coming from? This oscillation coming from because our electromagnetic torque is oscillating, because our current times the voltage, that term is fluctuating. So if there is an oscillation in an electromagnetic torque, but I don't want to see that oscillation in the speed, what do I do to the mechanical system?
Increase the time constant?
Increase the time constant. Perfect. How will I do that?
Increase inertia.
Increase inertia. So the easiest way to address that in a fan is make your blades large. Right? So you have large blades in your fan, that's going to increase your inertia. That way you can reduce your oscillation. So if you have a fan at your home and it's vibrating too much, you can swap out the blades with larger one or add some weights, make the blades heavier. That would smoothen out the oscillation that you see, vibration that you see, right? But in industrial system, this is not acceptable. We can't have this much vibration on a couple of kilowatt of motor because that's going to shake the whole thing. It's very inefficient. So let's look at what will happen when you have a two-phase system. So let's say we have some voltage Vm cos omega t. And then we have another voltage Vm, which is phase shifted by 90 degree sin omega t. And somehow both of these is going into some big motor and it's generating some power. So the power generated by the first, the power generated by the first one is going to look like this. Let's ignore the reactive component for a minute. Let's assume it's just all real power in the motor. There is no inductance or anything to excite. What will be the power? Let's say the current in both of these are the same magnitude. What will be the power due to the second source? Will it be in the same phase as the first one or will it be phase shifted? Phase shifted, right? Phase shifted by 90 degrees. So the power due to the second one is going to be like this. Interestingly, when you sum these two up, you end up with a flat power. Right? So you can, once you go home, put it in MATLAB, some cos omega t times the current, let's assume is some Im cos omega t minus pi t minus pi by 3 omega t, sorry. Cos omega t minus pi by 3. In this case, it will be Im sin omega t minus pi by 3. Right? So put sin omega t times sin omega t minus pi by 3 plus cos omega t times cos omega t minus pi by 3. And you'll get these two waveforms. That sum would end up coming out to be a flat value. Right? So once you go to two phase, you end up with this advantage that your power is no longer fluctuating. So if you can somehow make a motor that would take current from both of these phases and they are phase shifted accordingly. If this is phase shifted from this by 90, the current here must also be phase shifted from this by 90. If it is not, then the problem on its own, it won't sum up to be the constant. Then you get a beautiful system where the motor power going into the motor power is always a constant. Right? So then what it means, there is no pulsation in my torque, electromagnetic torque. There is no pulsation in my omega. Right? Have any of you seen any two-phase systems? Is two-phase system present in your homes? No? What was it, Thomas?
Sometimes,
Where?
I don't remember.
So if you go to your basement and you see a washing machine, the outlet for the washing machine looks a bit odd. Right? So your washing machine comes from, it's not a two-phase, commonly somewhat of a very odd phenomena, right? Just in the US. It's nowhere in Europe, nowhere in India. I don't know if it's in Canada, definitely not in China. All of those countries, even in India, we have either one phase or three phase. There is nothing called split phase. So in the US, what they do is they take a single phase transformer, which is on the telephone pole outside your home. And on the secondary side, they use a transformer with a center tap so that you get a voltage like this. This is going from 0 to 120 RMS, and another voltage which is 180 degree phase shifted. Right? And so effectively you'll get 240 volts RMS for high power application. So you would get all these three lines come to your house, and your certified electrician, what they would do is they would wire it in such a way that half of your house is in this and the other half of your house is in this. Or if you live in an apartment complex, one apartment will get this, the other apartment will get this, and your washing machine will get all three. Because it requires quite a lot of power. If you give 120 volts, the current is going to be too large. And if the current is too large, that's going to make the motor a little bit more complicated to design and going to become much bigger in size. So you want to limit the current. That way you use a larger voltage, the current will be high. If you double your voltage, your current can be half for the same amount of power. Right? So your motor can be a little bit smaller and more compact. So in those cases, we do the split phase, but this is not what two-phase motor is, because split phase is effectively just a single phase, because this voltage and this voltage is just another larger single phase voltage, right? So split phase is not to be confused with two-phase motor. So you would have seen a two-phase motor without realizing it's a two-phase motor in a fan. When the fan starts, a single-phase voltage, if you apply to a fan, it will never start at all. Yeah, we'll look at that tomorrow on Wednesday, why it won't. But so what they do is they initially have some kind of additional winding in the fan, which has a capacitor in series with it. So if I have this voltage and I put a capacitor in series with it, the voltage after the capacitor would be 90-degree phase shifted, effectively making it appear as if it's another two-phase voltage source, right? Just for a short instant of time. And then once the motor starts rotating, the other winding will be disconnected and it'll just run off of the single-phase system. Okay. So typically you won't see a two-phase system other than that. All other systems that you see are three-phase, right? So between one phase and two phase, we clear one phase and any polyphase. So if you go to two phase, three phase, four phase, five phase, doesn't matter. Power will always be a constant. One phase will always be pulsating. So any polyphase motor, phase greater than one, you have eliminated the problem of power pulsating. So why don't all motors use two phase? Why do they go to three phase? So before we jump into that, how many wires do I need for a one phase system? Two wires, right? So if I have a single phase voltage, sinusoid voltage, and I have some motor, I need one wire for the current to go through, one wire for the current to come back to. In a two-phase system, how many wires would I need? 4, 3, because I can merge. Say this voltage is negative here, positive here. So these two terminals can be shared. Right? So that's the advantage. So in this case, I have two wires carrying some power P. In this case, so two wires carrying power P. In this case, I have two voltage sources, so I can put double the amount of power. With 3 wire, I can transfer 2 times amount of power that I could do with a single phase network. So if I had just a single voltage supply, I had 2 wires and I would transfer some power P. If I had 2 sources, this is transferring some power P, this is transferring some power P. I can end up with 2 times the power, but with 3 wires. Right? If I go to 3-phase system, how many wires do I need? Let's assume it's completely balanced. 3 wires. For our motor, all the windings hopefully are balanced. In the advanced mode, we look at cases where the phase becomes unbalanced. It will cause some circulating currents and delta motors and so on and so forth. But for our case, we're going to assume all the phases are balanced. So we have a motor, I shouldn't be using red. So we have 3 wires. And we have some power coming through. And the way these are connected could be multiple options. Right, so we have 3 voltage sources supplying power to the motor. Let's take an example at any given instant time t. Let's say the current in the A phase is 5 ampere. Current in the B phase is, let's say, 5 ampere. What is the current in the C phase going to be? 10 ampere. Is it 10? Negative 10. Or 10 ampere in the other direction. Right? We don't need an external additional wire to close this network. As long as, again, this is balanced. Even if it's unbalanced, you don't need an additional wire. The voltage will become crappy if you don't have that additional wire, neutral wire. But the idea is we can have 3 wires and get the power into the system without any issues. And with 3 wires, we can transfer power. How much power can we transfer compared to the one-phase case? If in the one-phase case, we could transfer some power P, what will be the amount of power we could transfer in the 3-phase case? 3 times the power. Right, so because we had 3 voltage sources, same voltages as before. If the current there is shifted by 30 degree in the one-phase case, even in the second case, it was 30 degree for the first voltage, 30 plus 90, 120 degree for the second voltage. In this case, the voltages are going to be phase shifted by 0, 120 degree, and 240 degree. Right? And the currents would again be shifted 30 degree from each of those phases. So if you do the power product, you'll have individual 3 sine waves, cos 2 omega t terms, phase shifted by 120 degree, but when you sum them up, so if this was 1p in the one phase case, in two phase case, it will come out to be 2p, in three phase case, it will come out to be 3p. Right? So each wire in this case carries power p in the three phase case. In the two phase case, each wire carries the power 2 by 3. In the one phase case, each wire carries half P. Right? So for given copper wires, these transmission wires are running across the country. They're quite expensive. So you want to optimize how much power you can transfer for the amount of copper you lay out, right? Or aluminum wires that you lay out, typically aluminum strands. So the three-phase system gives you the maximum amount of power per wire that you put in your infrastructure. What will happen if I go to 4-phase, 5-phase, 6-phase? This is the upper limit. So you can go to any polyphase greater than 3, 4-phase, 5-phase. Because the idea is how much wires do you need to do for a 5-phase system? All of them share the same common return. And you have a 5-phase motor. So you have 5 wires, 5 times the power. So the power per wire is just 1. Okay. So that's why we settled at 3-phase system, because you can go higher, but you don't gain anything out of it. In EV applications, you do create 5-phase motors because they give you some amount of redundancy. One phase fails and you can still control the motor using the other 4 phases. In 6-phase, typically used, one phase fails, you can still use the other set of phases with reduced power. And the other advantage is you can remove torque pulsation by selecting the correct set of windings. But for transmission application, for power transmission, 3-phase is the one that makes the most sense. There is one more big problem with 2-phase system. Can somebody tell me? So let's say in each of these cases, we have some sinusoidal current. So this is carrying some current, 5 ampere. This is also, let's say, of course, has to be 120 degree phase shifted. Right? And the other one is going to be 240 degree phase shifted. Right, so this is 0, this is going to be 0.866, this is going to be root 3 by 2, negative. So this is what the currents are going to look like. I can draw it in phasors. We already know how to use phasors now. So let's say my A phase current is here. In phasor, where will I put the B phase current? What will be the angle between the A phase current and the B phase current? For the 3-phase network, 120. It's completely up to your choice which way you look at it is clockwise, which way you look at it counterclockwise. I like to put B on the other side. Power system people like to put it on the bottom side. Machines people on the top. And so the angle between the 3 is going to be 120 degree. What is going to be the sum of the 3 currents? 0. Right? If I sum up these 3 currents, where is it going? Nowhere. So the sum has to be 0. Right? ECM. I can look at it from the phasor diagram and come to the same conclusion. I have vector along this direction, vector along this direction, vector along this direction, all of equal length, all separated equally. So the sum would be at the right in the center. So think of it like a point and 3 of you are standing at 120 degree apart and all of you are pulling at the same force. That single point is not going to move anywhere. Okay? So that's how it's going to be. In a 2-phase system, I have a current IA here. What will be the angle between the current in the A phase and current in the B phase? For a 2-phase system? How many of you said 180 degree? Right? Any other answer?
It's 90.
90 degree, perfect. Leo, right? Okay. So if it was at 180 degree, we'll go to a split phase system, okay, which I said that is not a two-phase system. So this is a split phase motor. The current here is going to be, let's say, along this voltage, and this is the current in the other phase. They're 180-degree phase shifted. This is a split phase system. In effect, this behaves as just a one-phase system with a net higher voltage. Right? And we will see when we look at motors why we do put it at 90-degree and not 180-degree. Because if you put it at 180-degree, the motor won't even start to rotate because it becomes effectively behaves like a one-phase motor at that point. When you put it at 90-degree, you can create rotating space vectors which will start rotating the motor. So a two-phase system is actually separated by 90-degree, not 180-degree. Right? So we have our current IA here, IB here. What is going to be the direction of the, let's say this magnitude is same as this magnitude. How do I find the current at the return conductor? So in the phasor representation that I have, this current is some magnitude Im at some angle 0-degree, let's say, and this current is Im at some angle 90-degree in our phasor domain. What is going to be the total return current? How will we figure it out in the phasor using phasors? The reason we went to phases is so that we can do this diagrammatically without having to break our head. So how will you do that? What will be the sum? Just a vector addition, right through the middle. So the total return current, IR, which is going to be sum of this vector plus sum of this vector. This is going to be IR. Let's say this magnitude is 1 ampere. This magnitude is 1 ampere. What is the magnitude of the return current going to be?
1 times square root 2.
1 over root 2. Thank you. Right? Sorry, root 2, right? Square root of 1 square plus 1 square.
Yeah.
So we end up with 1.414 amps. And we could have seen the other way too. We could have looked at it from the time domain too. We had the sine wave. We had this other sine wave. Let's say this is the 45-degree angle. Right? The cos and the sine would intersect at that 45-degree angle. Here the sine would have been 1 by root 2. The cos would have been 1 by root 2. So the sum of the two currents would just be root 2. Either way you see it, you'll get the same answer. Whether you look at it in phasor or you look at it in the time domain. So this is the other big problem with the two-phase system. Not only is the power limited, but the third wire carries more current than the other two wires. At some angle 45 degree. Right, the angle itself is irrelevant. But in a three-phase system, all the wires carry the same current. In a two-phase system, two wires carry one amount of current. The third wire needs to be rated in a different way. So if you had a power system using two-phase instead of three phases, then you would have these wires, each of them being different from one another, which is very problematic because it increases your cost. When you order it in volume and all three wires are exactly the same, you get a significant cost saving compared to two wires being one rating and the third wire being a completely different rating. Right? So economically, it makes sense in multiple reasons to go to three-phase because you have each wire unity power. In case of two-phase, you get a slightly reduced power. One phase, it's worse. And then the other problem with two-phase is that the third wire carries slightly larger current, not slightly, almost twice the larger current than the other two wires. While in three-phase system, all the three wires carry the same current. Yep, Thomas.
When you wrote the first two currents both had 5 amps and then the last one had minus 10 amps.
Yeah.
That was at like an instant in time then.
At an instant in time.
Is average, they're all doing the same current.
Not an average, the magnitude of them.
Okay.
The magnitude would all be same. The average, they would all be zero because these are sinusoids. Right? So the phasor magnitude, when I drew their IA by the IC, those would all be the same for all the three of them. Okay, can you tell me what that, let's say the case where I had 5 ampere, minus 10 ampere. What would have been the magnitude of the phasor?
0.
Magnitude of this phasor, the single phasor. If I give you an time instant value of current, if IA is 5 ampere, IB is 5 ampere, and IC for a three-phase system is 10 ampere. And if I ask you, what will be the magnitude? So this is at one particular instance. I had some current like this, and I took a snapshot somewhere here, and I gave you the three currents for three different phases. Can you tell me what the peak of the currents would be?
Is it 10?
10 ampere. Because when you look at your three-phase current and voltages, if this is one of them and the other two, so wherever the other two intersects, the third one would be at its peak when you look at your three-phase voltages and currents. Right, so if the other two phases are given as equal, then the third one is representing the peak. Okay? So that's how the three-phase, because of the 120-degree phase shifts. Right, so easy way to determine that. We look at another way, given actually any instantaneous values, this value, if I give you in a three-phase system any two currents, as long as the third one is, the system is balanced, as long as there's no neutral current coming out, within just two currents, I can figure out exactly what the phase angle of the signal you have given me is. Because I can figure out what the third current is, and then I have three values, I can figure out what the phase angle is being at, right? With it, we are done. On Wednesday's class, we'll jump to the AC motors. Okay, those of you who participate in class, don't forget to put the note. Those of you sitting in the front, I remember the names, as I can see clearly. But those of you answered in the behind, I sometimes forget. So please do make a note of it and drop it off.